Let's look at this S sub n. Let's take some cases. Case 1, r is less than 1. If r is less than 1, what is the limit as n goes to infinity of a minus a r to the n over 1 minus r going to be equal to? So where is r to the n going to go if r is less than 1?
0.
It's going to go to 0. So I want you to zero out the r to the n here, which kills off this term and leaves you with a over 1 minus r. That's what happens if r is less than 1. Case 2. R is bigger than 1. What would the limit as n goes to infinity of a minus a r to the n over 1 minus r go to? This would be r to the n is becoming infinite, right? And so this thing diverges, right? You have infinity on top. The bottom is just going to be a number. So the top grows without bound, the bottom doesn't grow. And so this is going to diverge. What if r is 1? If r is 1, I want you to go back and look at the original geometric series. Forget all this crap we just did. This is the geometric series. What if r is 1? It's just a plus a plus a plus a plus a plus a plus a forever, and that's going to diverge. 2 plus 2 plus 2 plus 2. It doesn't matter what a is. 3 plus 3 plus 3. Negative 5 plus negative 5 plus negative 5 plus negative 5. That's going to grow without bound. It's going to be either infinite or negative infinity, but it's going to diverge. It's not going to go to a number, right? Diverge. Those are the only possibilities we can have. We're either going to have divergence or convergence. The only way we're getting convergence is if r is what? Less than 1. If r is less than 1, we're going to get convergence, and the infinite sum will be a over 1 minus r. That's what the sum will be. With that in mind, I'm going to summarize. In summary, for a geometric series, sum n equals 1 to infinity of a r to the n minus 1 is going to do one of two things. It's going to equal a over 1 minus r if r is less than 1, and it's going to diverge if r is greater than 1 or equal to 1. There are two possibilities with geometric series. It's either convergent or divergent. The r is what determines that. Now there's a little more that we could show. I'm going to skip over it. You know, verify it if you want on your own. You can change this to absolute value of r less than 1 and absolute value of r greater than or equal to 1. In other words, if your r is a negative number, this still holds. You just have to look at the absolute value of it. All right. That's the big result. All right. Now, go back to the example that we just had. Back to the example where we had 3/10 plus 3/100 plus, we came up with the formula for that. What was the formula? 3/10 times 1/10 to the n minus 1, right? That's what we had. What's a here? 3/10. What's r here? 1/10. Let's do a check on r. The absolute value of r is the absolute value of 1/10. That's less than 1, right? Therefore, this converges. What does it converge to? A over 1 minus r. What's a? 3/10 over 1 minus 1/10. 1 minus 1/10? 9/10. Flip, reciprocal. 3 over 9, 30 over 90, which is 1/3. That's it. Point 33333 forever. Isn't that nice? You need, for geometric series, you need them to have an r less than, absolute value of r needs to be less than 1 in order for it to converge. Beautiful. Find this sum. Sum n equals 1 to infinity, 5 to the n plus 2 over pi to the n times 3 to the n plus 1. I'm throwing you right into the fire here. So when you look at this, you're looking at this, you say, hey, this is an infinite series, right? I'm trying to find the sum of an infinite series. What are the different types of infinite series? Well, we have geometric, we have, that's all we have right now. Well, harmonic I haven't talked about. All we talked about is geometric, right? So chances are this is geometric. But later on, you don't know that. You have to be able to recognize it. So what are some of the characteristics that we look for in geometric series? The n is up in an exponent, right? The n is up in an exponent. A r to the n minus 1. That n is up here in an exponent. It's not down in a base. So I'm trying to get that to look like a geometric. So all I need to know, what's r, what's a, right? How do you mean split it apart?
5 times 5 to the second.
Okay, so you want to just start breaking those up first? That's okay with me. You want to make that 5 to the n times 5 squared. And then you want to make that pi to the n and then 3 to the n times 3. Does everyone agree that we could do that? Properties of exponents there? Questions? See if you buy this. What constant do I have? What's not controlled by n? 3 and 5 squared, right? So can I put a 25/3 out here? Like this? Yeah? And then everything else is raised to the n, isn't it? Everything else is raised to the n? So could I do this? 5 over 3 pi, that quantity to the n. Because the n would go on to the 5 and to the 3 and to the pi. That's the properties of exponents there. So that's fair? All right. What is your instinct telling you that r is probably going to be? 5 over 3 pi? The only problem you have right now is that this is n minus 1. and here you have n, right? So you might have to tweak that. But that shouldn't change what the base is. So before I go any further, is the r that you are looking at less than 1? Because if it's not less than 1, this is going to diverge, right? 5 over 3 pi. 3 pi is about 9-ish. 5 over 9, less than 1. So I'm feeling good that this will be a convergent geometric series. But I've got to make it look like that now. So this is where I come in with what? Minus 1, cheat. Minus 1 plus 1. Sum n equals 1 to infinity. 25 thirds. 5 over 3 pi to the what? N minus 1 times 5 over 3 pi to the 1, which you don't have to write, but I'm just going to write it just so you can see it. And then what I can do is I can take this, which is now just a constant, and I can put it out here with the other constant I had. Wait. Oh, 125. Okay. Yes. So you have 125, sum n equals 1 to infinity. 125 over 9 pi squared. No. Just, there's only 1 pi, right? This one didn't have a pi in it, right? So 9 pi, and then 5 over 3 pi to the n minus 1. Questions? Does that look like a geometric series? Yes? Okay, what's A for us? 125 over 9 pi. What's R? 5 over 3 pi, which is less than 1, right? So it converges. I could have put absolute value, but it's positive, so I'm not concerned. So this equals A over 1 minus R, like that. A over 1 minus R, which is 125, it's going to be weird looking, over 9 pi over 3 pi minus 5 over 3 pi. So I got a common denominator on the bottom. I'm going to flip, multiply. So this really just turns into 3 pi up here, and then 3 pi minus 5 down here. And these cancel, the pi's cancel, the 3's reduce. Y'all following me? Mm-hmm. Okay. This is gone, so what do we have? 125 over 9 pi minus 15. That looks right. Whatever that is. 9.41 something. All right. Good. What do you think? All right. What is that? Geometric series, right? Geometric series? You tell me, yes or no. Yes? That's the same? Okay, so I'm changing. I'm asking you for the first time to just consider the idea that we're going to start our index at 0. Just consider that we're going to do that. If I start this at 0, get AR to the 0, which is just A. Well, that's the question now. Does this notation create the same thing up there?
Yes.
It does, doesn't it?
Yeah.
So what I'm telling you is that if we allow some flexibility within our indexing, and we allow n to start at 0, then you could possibly have a different formula, a different format for a geometric series. And there are two commonly accepted forms of a geometric series. They are the two I've shown you. This one, or you start the index at 1, and you have to put an n minus 1 up there. Those are equivalent. Both of these give you the same thing. Do y'all see that? Do y'all agree that that would give you the same thing? Okay. So how would that come into play? Well, what if someone comes in here and gives you this, and they ask you to find, what this turns into? Let me see. Pi over 5 to the n, like that. So if we use this one, we have a problem, don't we? Because our index starts here at 0. We're used to seeing 1. But if you look at this form, then we can use 0, can't we? And then if we're using the 1 over there, we don't need n minus 1 up here anymore. We just need n, which we have. So do you all see that this right here is automatic, like it's ready to go right now? You know what A is. Well, maybe you don't know what A is. Do you know what R is?
Yes,
Pi over 5, which is less than 1, right? Check. What's A? 1, because there's a 1 in front of all these, so A is 1. So it converges? What would that converge to? A over 1 minus pi over 5. And then you could clean that up or just leave it. The moral of the story here is that be prepared to see geometric series given to you in two different formats. Yes?
What if it has n equals 0 as our index, but n minus 1 on the, is that going to just be automatically null or forward?
Let's see. You're saying what would you do in the case that someone gave you I'll make it pretty clean, 1/5 to the n minus 1.
Right.
So you're looking at that and you're like, okay, the n minus 1 looks right, but then it's not n equals 1. If it's n equals 0, then I need that to be n, not n minus 1. So can you make it n?
Yeah, plus
Yeah,
I could,
eat it, make it 1/5.
no, I could do that. I could do add 1 minus 1. No, that seems kind of weird. Couldn't I just do this? You just need an n there, right? Why don't I just write it like this? 1/5 to the n, 1/5 to the negative 1. That's the same as n minus 1? So what's 1/5? Yeah, what's 1/5 to the negative 1? It's just a 5. So this is just 5 1/5 to the n. Do you see that I now have it to the n? But now I've created an a, haven't I? And a is 5. So a is 5, r is 1/5. This will converge to 5 over 1 minus a 5th. Good question. Understand how that will work?
Yes, sir.
Good. You need to be ready to manipulate exponents here. Hidden ones, hidden zeros, add and subtract. Let me give you one that's a little bit more challenging. How about this one? Let's go 0. No, let's go 1. I'll make it hard. How about 5 to the n plus 1 over 8 to the 2n plus 1. Ooh. So you should be thinking geometric right now because you've got sum, infinity, all that junk. You got exponents that ends in the exponent. Are you going to want n minus ones or n's up there? N minus ones. Can you get an n minus 1 on the 5? Yeah?
Separate.
Okay. How can you rewrite that? 5 to the n minus 1 plus 1 plus 1. So really what I've done is I've introduced a 0 here, right? There was an n plus 1 up there. I did n minus 1 plus 1 plus 1. That's the same thing. So this is really 5 to the n minus 1 times 5 squared. Does anyone have any questions on that? Because, I mean, this is really like the fundamental thing we need to know. If we're having trouble seeing this, it's going to be nearly impossible to do the rest. Y squared, because what's left here is 2, right? That's a 2. The n minus 1 I used on this one, the 2 remaining ones I put together is a 2. So that's okay?
And you have it on the bottom.
What about the bottom? That's the harder one.
Couldn't you, it'd be n squared. If you split it apart, it'd be a2 n.
8. Okay, let's see. Can I do the minus 1 plus 1? Will that work? If I do minus 1 plus 1, and then I still had a plus 1 down there, that's not going to give me n minus 1, is it?
But you could just make plus 2 and then take 2 out.
You could do plus 2, yeah, yes, you could do that. I'm going to do something a little different, though. Watch. First thing I'm going to do is that. Do you agree with that?
Yes.
And then 8 to the 2n is really 8 squared to the n, and then that's just an 8. It's just going to come along for the ride. 8 squared, 64 to the n times 8 to the first power. And now can I make that minus 1?
Yes.
Yes, minus 1 plus 1. So this is 64 to the n minus 1 plus 1 times 8 to the first power. So we get 64 n minus to the n minus 1 times what? 64 to the 1 times 8 to the 1.
That's a big number.
Y'all see how I've done that? Sure. I'm going to be able to rewrite the entire denominator as 64 to the n minus 1 times 64 times 8. I'm going to be able to rewrite the entire numerator as 5 times 5 to the n minus 1. Right? No, 5 squared. So this should turn into sum n equals 1 to infinity 5 squared times 5 to the n minus 1 over the bottom, which is this. So 64 times 8 is what? 512? Yeah. Someone verify. I think it is 512. 64 to the n minus 1. We all good? Now the 5 to the n minus 1 and the 64 to the n minus 1 go together into one fraction.
That's your R.
And that's your r.
Yay.
And you got a, right? So sum n equals 1 to infinity of 25 over 512. 5 over 64 to the n minus 1. And that is in your geometric series form that you need. A is, R is 5/64, which is less than 1. So this is going to converge, right, to A over 1 minus R, which I'm not going to work through.
So basically, if you have this card, you can always.
I mean, you can do what you can to make it look geometric, yeah. Now let me just show you something. If I just put an n right here, you no longer have geometric. Even though everything else is geometric, that one n in there makes it no longer geometric. Well, that would be, yeah, we'll deal with that later. All right? I have 20 minutes or so, so I do want to talk about another series. You hate series already? Is that what I heard?
No, I
Oh.
said it's very good to see everybody like that we know, and then we know to like say hi.
Okay, how about, gosh, I'm on the fence about how I should do this. Harmonic series. This is what a harmonic series looks like. All harmonic series diverge. It is not possible for a harmonic series to converge. Now, I can try and explain why, but let's first get our heads around what a harmonic series looks like. All right, what if k is 1? What would, give me what harmonic series I'd get if k was 1. So here are some examples. If k is 1, this would be 1 plus a half plus a third, right, plus a fourth, plus dot, 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 forever. That's going to diverge. It becomes infinite. All right? I told you that, but I didn't explain why, correct? All right, let's let k be a different number. How about if k is 1/5? What if k is a fifth? What would you get? So imagine that this is 1/5. Plug in 1, what would you get? 1/5? Well, k is 1/5, so make it look like this instead. If this is 1/5, it would be 1/5 times 1 over n, wouldn't it?
Yeah.
That's what k being 1/5 would be. So you get 1/5 plus 1/10 plus 1/15 plus 1/20 plus forever diverges. Here's the basic idea behind a harmonic. If your denominator is growing linearly, right? This is going up, what, by 5 each time? 5 each time? That's linear growth. Here, the denominator is going up by 1 each time. So if your denominator keeps growing by a linear factor, then it's harmonic. So I always like to kind of summarize it this way. If you have sum n equals 1 to infinity of 1 over a linear expression in n, this is going to diverge. Can't write. Linear in n. So let me give you another example of a harmonic series. How about sum n equals 1 to infinity of 3n minus 2? So you could start plugging in 1, then 2, then 3, and start writing them out and try to add them up, right? But what you need to realize is that this is what? This is a harmonic series, okay? This is harmonic. And because it's harmonic, diverges. You're done. Exactly.
So
So on the test, if we saw, like, and we noticed it right away that it was harmonic,
You'd write harmonic,
diverge.
diverges.
So,
That's it.
but you're going to probably be a little tricky with that.
No, you need to recognize when you see harmonics. I mean, they come up, so you want to make sure as soon as you see one, okay, it's harmonic, done, diverges. So that's a lot easier than the geometric was, right?
Yeah.
Okay. Now, what would happen, though, if I changed it to like n squared? That would not be harmonic anymore because it's not linear in n. You need linear in n for it to be harmonic. We'll deal with that in a minute. That's going to be called a p-series. But one thing at a time. I think I have just enough time to show you an example of something that's kind of cool. Do you all know what an irrational number is? Describe to me what an irrational number is if I were to try and write it out. Like, what is it that makes it irrational compared to a rational number?
It can't be a fraction.
It can't be a fraction. Very good. So like, if I write pi, right, is approximately 3.1415, blah, 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 blah. The pattern here is that there is no pattern, okay? This never repeats, it never stops. But if you take a fraction, which are called rational numbers, like 4/5, that's going to do what? What's that as 0.8? 8/10? 0.8 is 4/5. So it's a decimal that stops. If I do 1/3, it's 0.333. This never stops, does it? But it repeats itself, right? It's always 3, 3, 3, 3, 3, 3, 3. So when you have irrational numbers, all irrational numbers never stop, never repeat, right? All fractions must either stop or repeat at some point. So we call this a non-repeating, non-terminating decimal. This is going to be a terminating decimal. This is a repeating decimal. Understand? That means if I give you a decimal that does repeat, you should be able to turn it into a fraction. So let's take this as an example. Convert to a fraction. Point 0.215, 215, 215, forever. That's the pattern. So that should be able to be written as a fraction because it repeats, right? So you could go on your calculator and you could actually, I think there's a button that goes like from decimal to fraction, and it might work, but it's not the point, right? Here's what I'm going to do. I'm going to write this out as being well, let me do it this way. This is actually 2/100ths. Let me write. I want to do one just a little bit different. What is the part that's repeating? 215, 215, 215. So could I write this first part right here as 215 somethings? What? Thousands. So you're getting that tenths, hundredths, thousands, 10,000ths, right? So 215 10,000ths. Plus this next one would be 215. So this was 10,000ths, 100,000ths, millions, 10 millions. So 215, these are place values, right? I think I got enough there. Is that right? This one had 4 zeros, didn't it? This one has 7 because I'm 3 more over. 215, 3 more over. So the next one should be 215 over. Yeah, let's not even care about what it is anymore. Let's just talk about it's 10 to what power? How many zeros did we have here? 4, so that's 10 to the 4th. This is 10 to the 7th. This is 10 to the 10th, right? 10 to the 10th. The next one will be 215, 10 to the 13th, and so on and so forth. Yeah? Now I'm going to go backwards, and I'm going to rewrite this as 10 to the 7th. I'm going to rewrite this as 10 to the 4th. Anybody know where I'm about to go with this? I'm going to come up with a formula. I'm going to write this in sigma notation. Okay, so let's try and write this as a series. Series, let's see, n equals 1 to infinity. All right, what never changes? 215. Always on top? 215. And then all of the denominators are 10 to some power. And look at those powers. The powers are 4, 7, 10, 13. So think back in the previous section. If I put this down and asked you to come up with a formula that would generate 4, 7, 10, 13, could you come up with a formula that does it? What are these all multiples of, almost? I mean, what do these all go up by each time? 3. So you can almost look at it as like they're multiples of 3. They're not quite, though. 3, 6, 9, 12, right? Do you see that? 3, 6, 9, 12. These are all one more than a multiple of 12. So hold on. 10 to the 3n plus 1. It's hard to teach that part right there, how to recognize that. You see it, though? Okay, so you look at that and you go, well, that looks kind of like a geometric series. Because I've got n is in a power, right? Yeah. So I've got to get this to look like a times r to the n minus 1. 215, let's just move that out front real quick. I'm not saying that's going to be a. In fact, I know that's not going to be a. And then I'm going to write 1 over, how about 10 to the 3n times 10 to the 1? And then I can take that 10 out under the 215. Any questions here? No? Okay. So I can take the n out, or the 10 out under the 215. Don't write that as a decimal, 21.5. I mean, we want to keep everything as fractions. We want everything exact. And then I have, what over here? 1 over 10 to the 3n. Can I rewrite that as 1 over 10 cubed to the n? And that's really 1 over 1,000 to the n? Agreed? Yes. And could I rewrite that as 1 over 10,000, or sorry, 1 over 1,000 to the n like this? That's a critical step right here. You were all agreeing with me that this became this. 10 cubed is 1,000, so 1 over 1,000 to the n. But I can write 1 over 1,000 to the n as 1 over 1,000 all to the n, because if you take the n and put it on the 1, what is it? 1. So these are equivalent, right? This is the same as this. And that, I believe, is starting to lead us to what r is going to be, right? R looks like it's going to be 1 over 1,000. But I don't quite have it, right? What do I still need? Minus 1. So I need to do maybe minus 1 plus 1. Minus 1 plus 1. And so we get sum n equals 1 to infinity. We're almost there. 215 over 10 times 1 over 1,000 to the n minus 1 times 1 over 1,000, right? To the first power. The 1 over 1,000 is going to go out over here. So that's going to become 215 over 10,000 And then 1 over 1,000 to the n minus 1. And that is exactly the geometric series that I need, right? That's the form, a to the r, a to the r. A times r to the n minus 1. So what is a? 215 over 10,000. What's r? 1 over 1,000. Is r less than 1? Yes, this should converge. And it should actually converge to a 10 to the fourth over 1 minus r. I'll do 1 over 1,000. I just need a common denominator here. So 1,000 over 1,000. Put them together, you get 999 over 1,000. I'm going to write 1,000 as 10 cubed. That okay with you? And then flip this 10 cubed over 999. And I get 3 of these factors to go away, right? So this is gone, and this 4 becomes a what? A 1. So 215 over 10 times 999, which is 215 over 9,990. So if you have your calculator, type in 215 divided by 9990. 0.0215215215. That's it. That's how you can check that you got it. This is a great problem, okay? I like this problem because there's a lot of little things in here. It knocks out a lot of different concepts. I realize you can do this on your calculator probably, have it do it, but I've always liked putting those on tests. All right, we still have a lot to do in this section, so we're not anywhere close to being done with 8.2. I would say for homework, page 443, you can handle 7 through 12. You can probably do 31. 33 might be a little bit messy. I'll give you a hint on 33. This is all messing with geometric right now. We still have in this section, we still need to talk about, oh, is that the next section? Hold on. No? We still need to talk about what are called telescopic series. Yeah, there they are. Telescopic, or what are called collapsing series, we still need to talk about in 8.2. But on 33, they give you something like, it would, like on the problem I just gave us, it would be like 3.0215215. So the difference is that they gave you this 3 out here. So you do the whole problem the same, but you would just look at this as being 3 plus all this junk, right? So you would go through and you would get your answer, which we got this, 215 over 9990, and then you get a common denominator and add the 2 together. That would be the difference.
Can you ignore the 3 till the end of the
Till the very end, yes. So whatever this number is out here, you can ignore it. Just work with this tail part, then add at the end. All right, everyone, that's it, right? We're done for the week. Everything I've talked about today will definitely be on the test, which is on Thursday. All right, let me turn my camera off. Go.